This is Algebra 2, Semester 2, Unit 12, Section 7.6. Okay, in this section, what we need to look at is that exponential equations, if you have the same base and you've got exponents up here, for example, well, here's a great example right here that I gave you. 3 to the 2x equals 8. That means that the 2x would equal 8 because 3 to the 8th is only equal to 3 to the 8th, if that makes sense. So that 2x has to be equal to 8. Now that only works if b to the x equals by, then that's the only time that it works that x would equal y. Okay, both have to be occurring there. So when we come down to the problems that they'd like us to work, we're actually looking to get the base the very same. So we look at 4 and we look at 2, or 1/2, and we say, how can we write those with the same base, 4 and 1/2? Well, it looks to me like we could possibly use the base 2. 4 is equal to 2 to the 2nd. 1 over 2 is equal to 2 to the negative 1. So, in our equation here, 4 being equal to 2 squared, we write that 2 to the 2x. Just bring that x right on down. With the 1/2, now we say 1/2 is equal to 2 to the negative 1st, so we're going to have to bring it down, 2 to the 2x, that was your 4 squared. 4 is 2 squared, so 2 to the 2x equals 2 to the, remember this is a 1 down here, bringing it to the top is a negative 1 times x minus 3. Now what we have is we have bases that are identical. Because of that, we can ignore the base and solve for the exponent. So we have 2x equals negative 1 times x minus 3. 2x equals negative 1 times x is negative x. Negative 1 times negative 3 is positive 3. Draw the line down. We're going to add x to each side. So we get 3x equals 3. Divide by 3 on each side. And we see that x equals 1. Okay. Okay. And the next problem. We have 9 to the 2x equals 27 to the x minus 1. Well, we're looking at the bases, 9 and 27. We need to make them with the same base. 9 can be written as 3 squared. 27 is 3 cubed. So now in our equation, we can simply replace the 9 with 3 squared. Go ahead and bring down your 2x that 9 was being raised to. And now 27 can be written as 3 cubed and bring down the x minus 1. Okay? So we have 3 to the 2 times 2x would be 4x equals 3 to the, distribute here, 3x minus 3. Okay. Our bases are the same. We can ignore them and we can go straight to the exponents. 4x equals 3x minus 3. We subtract 3x from each side. Get that x alone. That would cancel. We get x equals negative 3. Okay? X equals negative 3. Next set of problems. Not sure how well you're able to see this. I'm bringing in just a little bit closer. Okay, there we go. Our bases are 100 and 1,000. So we ask ourselves, how could these be written with the same base and different exponents? Well, we know that 100 is 10 squared, and we notice that 1,000 is 10 cubed. Those are both common exponents that I've asked you to memorize, so hopefully you do remember those. So now we bring back in the 10 squared in place of the 100, so we'd have 10, 2 times 7x plus 1 equals 10 to the third times 3x minus 2. Okay, so now we can ignore the bases and we go 2, 7x plus 1 equals 3 to the 3x minus 2. Okay, what would you say you would think we should do on the first step here? If you said distribute, you're right on. 2 distributed into this binomial would become 14x plus 2. The other side distributed would be 9x minus 6. And now we gather the x's to one side. We get rid of them on the right side usually. So minus 9x over there, minus 9x here. This cancels. And we get 14 minus 9x is 5x plus 2 equals negative 6. Now we want to get that creepy dude alone again. If you're remembering back to Algebra 1, we get that guy all by himself. We subtract 2 from each side. That wipes out. We get 5x equals negative 8. Okay, now we divide by 5 on each side. Still trying to get that guy by himself. We finally have him alone, and we have a negative 8/5. Okay, down to the next one. We have 81, and we have 1/3. And we're asking ourselves, how can we write these with the same base? Well, 81 is 9 times 9. Break that down, it's 3 times 3 times 3 times 3, so it is 3 to the 4th. Well, that helps us significantly because 1/3 is 1 over 3 to the 1st. We know if we bring that 3 to the 1st to the top, it's 3 to the negative 1st. So we now have the same base if we use those exponential factors there. So we come over and we replace 81 with 3 to the 4th. Go ahead and bring down the exponent from the 81. So it's 3 minus x equals 3 to the negative 1st will be negative 1 times 5x minus 6. Okay. The bases are the same, so we get rid of those. And we have 4 times 3 minus x equals negative 1 times 5x minus 6. Okay. Now we need to distribute. 4 times 3 is 12. 4 times negative x is negative 4x. Negative 1 times 5x is negative 5x. Negative 1 times negative 6 is a positive 6. Now we gather our creepy dudes to one side. I would get rid of them over here personally. I always like to get rid of them on the left or on the right. I don't know why that is. I bring them to the left. That cancels. A positive 5x and a negative 4x leaves us with one positive x. And we have 12 out here and 6 left over here. Now we subtract 12 from each side. That cancels, and we get x equals negative 6. In class, we're going to go through and I'll show you how to check these. I just wanted to make sure that we got through the basics on here. The next kind of problem is when you're given an exponent with a number that you can't see a way to make their bases the same, and it doesn't have an exponent other than 1. And I just wanted to bring in what we discovered in a previous rule. If we were to bring in a log base 4 with this 4 to the x, do you remember the rule where we can eliminate, or it cancels out, the log 4 with the base of the exponent? In other words, if we have log 2, 2 to the third, and we're saying, well, what's the answer to that? Log 2 of 8 is 3. So we discovered the other day that we can just eliminate those, reduce them like you do with a fraction, and you end up with your answer being 3. So when we have log 4 and 4 to the x, we know the answer to this whole thing. We reduce the 4 and the log 4, and we have x over here. Now, because we brought a log 4 in on the left-hand side of the equation, because we have this log 4 on the left-hand side, we also need it on the right-hand side. So we have to bring in a log 4 11 there. What you do to one side, you have to do to the other. Well, that means that x is equal to log 4 11. That might not look like we got anywhere, but we kind of did, because yesterday we discovered that we can change base and make that log 11 divided by log 4. And we can actually plug that into a calculator. And we would actually take, don't know if you can see this screen. Okay, we would look at the keys and we would go to log 11. Now if you look at the screen, it's got a parenthesis at the beginning. Make sure and close that parenthesis. That was the only difficulty some of you were having in class. Now move on to saying, okay, we want to divide by log 4. So we hit the divide button. And now we go back to log 4, close the parenthesis. There's what we have. And when we hit enter, it will give us an answer. Now, just round that off, probably to the second digit, probably to the hundredths place. So 1.73 would be close enough. So x is equal to 1.73 approximately. Okay? So this is what we're going to do in all of these on the next page. So we're going to get rid of our base 2 here by bringing in a log 2. What we do to one side, we have to do to the other. So we have log 2, 5. Okay. Now the log 2 and the 2 cancel. And we have log 2, 5 equals x. Now we do our change of base. And we go x equals log, the way that you guys remembered how to do these the other day is the base down here goes to the bottom, so it's log 5 divided by log 2. Okay, if you do not have a calculator that you can put logs into, you can calculate these when you come to class, just leave them that far along. Okay, let's go ahead and do the next one. It would be log 7 in order to cancel that base of the exponent, or base of the power. So we bring in a log 7 on this side. And now we say, okay, the log 7 and that power base cancel, and we have 9x equals log 15 over log 7. Well, when you put that into the calculator, you've still got to figure that doesn't equal x yet because we've got 9x. So what do you think you'd do on each side to get that x alone? If you said divide by 9, you are absolutely correct. So proud of you. You are doing some good math. So we have x would equal log 15 over log 7 divided by 9. So you're going to divide each side by 9. So that's what your final equation would be. Get an approximation when you get into class from the calculator. Okay. Last one, we'll rewrite it up here a little bit. Now this is your natural log e base. Okay, so let's just start over up a little bit higher so we don't run into that box on this one. So we have 4e to the negative 0.3x minus 7 equals 13. Before we can actually start working on the exponents, we need to go ahead and get rid of this 7, a negative 7. So how do we get rid of a minus 7? We add 7 to each side. That cancels, and we get 4e to the negative 0.3x equals 20. Okay? Now, in order to get that e alone, which is what we really want to do, is we would divide by 4 on each side. Now we have base e, or Euler's number, to the negative 0.3x equals 5. Now in order to cancel e, remember that would be a log base e, but we write that as ln. So we have ln e negative 0.3x equals ln 5. What we do to one side, we have to do to the other. That's where we get that. Now that means that these two will cancel. It's just like when we have a log 2 and a 2 to an exponent. E and the ln cancel each other. So we end up with negative 0.3x equals ln 5. To get the x alone, we'd divide by negative 0.3. What we do to one side, we have to do to the other. So we have x equals ln 5 divided by negative 0.3. And you can actually put this into the calculator. If you look on the keys, right here's the ln. So you're going to come in and you're going to punch in the ln 5 and then divide it by negative 0.3. Okay, last little section, and then you'll give me an approximation. X is approximately equal to, and fill that in tomorrow on that calculator. Okay, next little section here, we have if b and y are positive numbers, and b is not equal to 1, then log b to the x equals log b to the y if and only if x and y are equal. Okay? So, good example here. If we have log 2 to the x equals log 2 to the 7, that's only going to be true if x is equal to 7. Okay? So, now we can solve these kind of problems. If we have log to the 5th, or log base 5 to the 4x minus 7 is equal to log base 5 x plus 5, these log base 5s can cancel side to side. And we simply solve 4x minus 7 equals x plus 5. And that's just a basic algebra problem again, where you gather your x's to one side. If you were saying that you would subtract x, that's the way I would do it too. So we have 3x minus 7 equals 5. And now solve from there. I don't think that I need to step you through that part. If you don't get 4 as your answer, then make sure and ask at the beginning of class. The next one, if we have an ln on this side and an ln on that side, basically we're dividing by ln is a way that you could look at it. We just cancel them out side to side. Now we have 7x minus 4 equals 2x plus 11. And go ahead and just do the algebra to get your x's alone and solve. First step that I do is subtract 2x from each side. So we have 5x minus 4 equals 11. That one canceled. So go ahead and solve that. If you do not end up with x equals 3, again, put it on the board when you first come into class. We'll go over it. Okay, next problem here. Next problem. Well, we need to get rid of that log 4, but there isn't a log 4 over here, and we can't just bring one in. So, remember this property that says that we can cancel. If we have 4 raised to the log 4, they reduce each other. So we can bring in the base of an exponent, bring in the same base of an exponent on this side, and we end up with 4 and log 4 being able to cancel. So now we have 5x minus 1 equals 4 to the third. 4 to the third is 64. And now I think that you can solve that problem. You should come out with x being equal to 13. Again, if you don't, post it on the board when you come into class. We'll go through that. Okay, here we go. How can we get rid of that log 2? Again, we can raise it as an exponent. We studied that property in a previous video, and we've talked about it in class now. So this will reduce that. What you do to one side, you have to do the other, so that makes that 2 to the 5th. X minus 6 equals 2 to the 5th, which is 32. And then you'll go ahead and solve that. Should have added 6 to each side on that. So you would have x equals 38. Okay. Next one. Well, this one looks a little bit more complicated probably, because all of a sudden we're seeing, oh, wait a minute, we have a plus in between these, and we still need to get rid of those logs. So the first thing we have to do is use our skills that we've practiced with condensing. Plus would mean that they're being multiplied, so we can write one log to the front of them, and we can take 2x times x minus 5. Okay, equals 2. We haven't done anything to change the equation, we've just condensed that back. So the next thing is now to say, well, this is log base 10, so if we raise it by a power of 10, then we'd have log 10 as the exponent, 2x, x minus 5, equals 10 raised to the 2. So we've taken this equation and we've put it all into the exponents. Now this log 10 and that 10 canceled, that's why we did that move. And now we have 2x, x minus 5, and we see that it's equal to 100, because 10 squared is 100. Well, now we need to multiply this out. 2x times x would be 2x squared. 2x times negative 5 is negative 10x equals 100. Now we subtract 100 from each side because we have a quadratic and we need to factor if we can. So we have 2x squared minus 10x minus 100 equals, now there's nothing left over, there's 0. Okay, so first thing that we can factor out of there is a 2. 2 would go into all of those, so we divide everything by 2. We get x squared minus 5x minus 50 equals 0. Now we can factor using our shortcut from way back in chapter, wow, when was it? Back when we were doing chapter 8, we started factoring polynomials. You guys have done so great with those. So in factoring these, put the x in the front and we ask ourselves what numbers multiply to be negative 50 and add to be negative 5. Well, our factors of 50, we come over here, factors of 50, be 50 and 1, 25 and 2, 10 and 5, and right there we see the difference being 5. So we come back and we say, well, we have 10 and 5. The larger one will carry the sign of that middle term. So that's a negative 10, positive 5. Okay? So we have that still being equal to 0. And remember from our product property of 0 is that if two numbers are multiplied together and they equal 0, then one of these numbers has to be equal to 0. So we have x plus 5 equals 0. Subtract 5 from each side. And we have x equals negative 5. Or we could have x minus 10 equals 0, x equals 10. Now, with these kind of problems, we always have to check for extraneous situations, which means extraneous solutions are solutions that won't make the equation true. We've done all the math right, but they won't make it true. So we come up here and we plug in that negative 5. that would make it log 2 times negative 5 would be negative 10. There is no such thing as a negative number here for a log because we can't get a negative number when we're raising numbers to a power. So x equals negative 5 is extraneous. I would just mark it as EX as you mark it out. That means it can't occur. Now for the other one, we're saying log 20 plus log, we plug 10 in there, 10 minus 5 is 5, log 5 equals 2. You can actually plug that into a calculator and calculate it out and see if that's true. You should do that. Okay, last one on this page. Log 5x plus log x minus 1 equals 2. Again, we condense it. Plus means times, so we have log 5x times x minus 1 equals 2. We've done nothing. We haven't brought anything in, so we don't need to be duplicating anything. Now, this is a log to the base 10, so we know that we can raise that to a 10 power. Move our equals down, and we won't even have to rewrite it. Raise it to a 10 power on each side. This 10 and that log 10 there will reduce, and we have 5x times the x minus 1 equals 10 to the second, which is 100. Now we have 5x squared minus 5x equals 100. We subtract 100 from each side. 5x squared minus 5x. Subtract 100 minus 100 from each side equals 0. Factor out 5, or divide everything by 5, because we see it can be reduced. And we would have x squared minus 1x minus 20 equals 0. Go to our shortcut for factoring. Bring in x and x. What numbers multiply to be negative 20 and add to be negative 1? Be a negative 5 and a positive 4. X minus 5 equals 0. That's only going to happen when x equals positive 5. X plus 4 equals 0. That's only going to happen when x equals a negative 4. So now we need to go back up and decide which of these might be extraneous. So we plug them in here. Log 5 times negative 4, that would be a log negative 20. So we know that that one is undefined. So we come down and we put a line through that x equals negative 4, and we write that's extraneous. Okay, now we come over and we say log 5. Well, could that work? Log 5 times 5 would be 25 plus, now we plug 5 in for this one, 5 minus 1 would be log 4. When you come in, grab a calculator and type in log 25 plus log 4 and see if it equals 2. If so, then you're in good shape. Otherwise, that's also an extraneous solution. Okay, I believe that is the end of this section. See you tomorrow in class.